Okay, students, Assalamu alaikum. Today we are going to start our lecture regarding the application of momentum principle in fluid mechanics. In our last class, we developed a very important theorem, which is known as the Renault transport theorem. Uh, and then we utilized the Renault's transport theorem to actually solve problems related to continuity equation. So here it is going to be a continuation of what we studied or what we developed in the last class. That is using the same Renault transport theorem to actually develop the momentum equation and then use the momentum equation in the fluid flow problems to solve for the different forces associated with the fluid flows. So basically now we are moving towards kinetics. Previously we started from the kinematics, but right now we are actually moving towards the kinetics. And you know the difference between the kinematics and kinetics. When we talk about kinematics, we only deal with the velocities, acceleration, position. So regarding the flow, the factors or variables associated with the flow, we only discuss that, and the reasons and the cause behind that flow, we ignore it. That's in kinematics. But when we talk about kinetics, so we also deal with the forces which are actually involved in the motion, in the fluid motion. So anyways, now we are actually moving towards the kinetics of the fluid mechanics. So this chapter is chapter number 6 from your textbook, which is about the momentum principle. So we're going to continue, or we're going to deal with it now. So basic outline, the things that we are going to cover in this chapter will be the Newton's second law of motion. Then we will be discussing about the body and surface forces. We will also discuss about the linear momentum equation. But then some of the common applications of this would be on the fluid jets, nozzles, vanes, pipes and bends. And these are the areas that we are going to cover. Then after that, we're going to discuss a little about the Navier-Stokes equation. So these are the topics that we are going to cover in this chapter. So let's just start from this point onward. Fluid particle. The sum of force acting on a particle is proportional to the acceleration, and the constant of proportionality is the mass of the particle. Now, there is one very common fundamental principle that you have studied in the course of statics and in your basic physics from your secondary class, which is the Newton's second law of motion. What is the Newton's second law of motion? There is a specific equation which is actually defined by the Newton's second law of motion, and that equation is F is equals to ma. Very common equation. Okay, that is used in the Newton's second law of motion. Now we're just going to work over this equation so that we develop something related to the momentum. Okay. Now, what is acceleration? Acceleration, I can write here, it's differential of velocity with respect to time. This is right. This is acceleration. So I can write here F is equals to ma, can be written here as F is equals to m dv by dt. Right? F is equals to m dv by dt. Or we can write this as d by dt, because mass is constant, right? It's a constant of proportion. So constant can go inside the differential as well. So we can write here as d by dt into mv. So what will happen if you differentiate mv with respect to time? Okay, so mass is constant, is going to come out, and it will be just dv by dt. So if you differentiate mv with respect to time, you are going to get m dv by dt. right? And this is actually the same as ma. So our Newton's second law of equation, which is F is equals to ma, can also be written as F is equals to d by dt of mv. Now mv is what? mv is moment. This is momentum. So here we get one very significant principle, which says that rate of change of momentum, d by dt of mv means what? It means rate of change of momentum with time. This thing is equals to the force. Okay, now what is momentum? So you have anything moving with a certain velocity, and that thing has a specific mass. So the product of the mass and the velocity is the momentum. The momentum will be large if an object is moving at a very high velocity. Momentum will be small if an object is moving at a comparatively lower velocity. On the other hand, momentum will be large if an object has a huge mass. Momentum will be small if an object has a very small mass. So it's basically a product of these two terms, mass and the velocity. So that's the momentum, okay? So when you're saying what is the force, we're saying rate of change of momentum. So if the momentum is changing of something, that is basically equals to the force. And why does the momentum change? It's because of the force. The mass is not going to change, obviously. It will be the velocity that's going to change. But anything, what is Newton's second law of motion? If anything is moving, its velocity is not going to change until and unless some external force is applied. Anything moving keeps on moving, and its speed does not change until and unless an external force is applied. This is second law of motion, right? So this is what it said here as well, that the momentum of anything does not change until and unless some external force is applied. And how much will be the change in momentum? That depends upon how much is the force applied. How much will be the change in momentum? That will be based on how much is the force applied. So if you want to know that what are the forces involved, we can check how much is the change in the momentum. Or the other way around, if we apply certain forces, we can estimate what will be the change in the momentum. So in the fluid flow problems, we go both ways. Sometimes we see that the fluid velocity is changing, so we can estimate that what would be the forces in effect that could be responsible for the change of the fluid velocity and the momentum. Or the other way around, sometimes we apply forces, and then we need to figure out that what would be the effect in the change in the momentum. But right now, the momentum is important here because the rate of change of momentum, it's not just the momentum, the rate of change of momentum is actually directly linked with the forces applied. So do you get the relationship between the rate of change of momentum and the forces applied over the fluid system? So this is what's discussed here. Summation F is equals to ma, which is equals to d by dt mv. Okay. So this mv is basically, I can write here as capital M, which is the momentum. So because of a flowing fluid, because a flowing fluid involves many particles, the total external force is due to the rate of change of momentum of all the particles. Okay. So rate of change of momentum of all the particles is going to provide us what will be the total force. Okay. So this is what's mentioned here. Total external forces is equals to d by dt of momentum. Okay, and this should be summation of all the momentums, obviously. Now let's discuss forces one by one. There are two different kind of forces. One are known as the body forces, the other are known as the surface forces. Okay, force is basically what? A push or pull interaction between two bodies. According to Newton's third law of motion, force occurs in a pair as action and reaction. That is, they have equal magnitude but opposite direction. force can be categorized as body or surface forces. Okay, so let's talk about body force. Body force are the forces that act without physical contact, or termed body forces, are termed as body forces. For example, magnetic, gravitational, electrostatic forces. So for example, I'm standing here, there is gravity acting on me, which is pulling me downward. So there is a force of gravity which is acting on me, but that force of gravity is not having a direct contact with my body. It's acting on my body, but there is no surface to surface contact. Okay. Similarly, if you have an electromagnetic radiations, or similarly, if you have a magnetic field. So if something goes through that magnetic field, there is a specific force, electromagnetic forces, which are being applied. But these forces are there because of the field. Here we are in the gravitational field, so we are exposed to that forces, but they are not applied surface to surface. They're applied generally over the entire body. Okay, so these are known as the body forces. On the other hand, we have a second category, which is the surface forces. Now, surface forces requires physical contact, surface to surface contact. Okay, so they result from the surroundings acting on the controlled surface. For example, pressure. Pressure can only be applied when certain fluid or gas comes in contact with the surface. If it does not come in contact with the surface, that surface does not feel the pressure. Okay. Similarly, shear, buoyancy is there when an object is in contact with the fluid, when it enters into the fluid. Then the buoyancy force acts. There is a surface to surface contact, surface of the fluid in contact with that object. Okay. Lift, drag, surface tension, thrust. These are all the surface forces which require surface to surface contact. Okay. Otherwise, if there's no surface to surface contact, these forces cannot act. Rather, on the other hand, body forces, they do not require surface to surface contacts. Okay. So what can be asked in the exam? You can be asked in the exam that what kind of forces are there? How do you categorize those forces? Give examples related to those forces. So that could be a short question in the exam. Okay. So then you have to mention that basically the forces are categorized as into two different classes. We have body forces, we have surface forces. What are body forces? What are surface forces? And what are the examples of them? Okay. So this could come as short question. Note that when calculating pressure forces, the gauge pressure is used. Okay. So normally, if the gauge pressure means if it is just atmospheric, so atmospheric gauge is considered as 0. Okay, so if it is high pressure higher than the atmospheric, then obviously we're going to use how much higher than the atmospheric. That's the gauge pressure we're going to use in the calculations. So far, everything is clear? So this is also mentioned the same thing. Force, we have the body force, we have surface force, body force. There are a few examples of the body force. Then surface forces could be with the fluids, could be with the solids. When we are talking about the fluids, it could be pressure force, shear force, buoyant force, lift, drag, surface tension, thrust. When we're talking about the solids, then there is a friction force between different solids. Then we have tension, we have applied force, spring force, support force. These are some of the examples of the forces. Okay, now just to recall back that what we have studied in the last class, this is the Renault transport theorem. This is the Renault transport theorem. And the Renault transport theorem actually give a connection or combines the Lagrangian approach with the Eulerian approach of fluid flow analysis. Okay, so the Lagrangian approach says that we fix a specific mass of the fluid and then we analyze what's happened with that mass of the fluid. On the other hand, in the Eulerian approach, we does not fix a specific mass of the fluid. Rather, we specify a certain space, as a certain volume in space. Okay, and then we analyze that what fluid particles are passing through that volume and how the fluid properties are changing, or what are the variations in the fluid properties as they pass through that specific space. So in the Eulerian concept, we have a specific control volume which is given the consideration, but in the Lagrangian approach, we have the specific control mass, which is given the consideration. And here, the Eulerian and Lagrangian approaches are both linked together in the Renault transport theorem, which says that whatever the change occurs in a specific control mass is equal to whatever the change occurs in the control volume occupied by that control mass, plus whatever the change that occurs at the boundaries of the control volume, that is the control surface. Okay, so you have something that is going to occupy certain volume. So whatever the change is occurring in that volume, that is your control volume, plus whatever the change occurring at the boundary of that volume is equal to whatever the change occurring in the mass of that volume. Okay, so when we are focusing over the mass, this is the Lagrangian concept here on the left-hand side of the equation, and on the right-hand side of the equation, we have the Eulerian concepts. So these both terms are linked with the control surface. Okay, so here right now, when we are going to apply the Renault transport theorem over the momentum, so our extensive property will be the momentum itself. So we can say that capital B is our momentum here. So if our extensive property is the momentum, which is basically mass into velocity, now we can find out what will be the intensive property. Intensive property is always that extensive property divided by the mass. So the mass is going to cancel, and we're going to end up with the velocity. Okay. So here, when we have this extensive property B, we are going to replace it by capital M, and wherever we have these intensive properties, a small b, we are going to replace them by velocity. So if we do like this, so what do we have here? Then we will have d by dt of the momentum. So rate of change of momentum is equals to rate of change. Now we have this term here. This is the accumulation term of the momentum that we discussed earlier. Whatever the changes in the momentum occurring within the control volume. And then we will have another term here. This term will be the changes occurring at the control surface of the control volume. The surface which is surrounding the control volume, that is the boundary of the control volume. So in that surface, whatever changes are occurring, it will be represented by this term. So, but here, since we have now replaced P with the velocities, so we'll have the momentum terms here. Okay. Now, rate of change of momentum itself is equals to or depends upon whatever the external force is acting. So we have just discussed this in the earlier slide, that rate of change of momentum is equals to summation of the external forces. So we are going to substitute it here. So our equation becomes this. Summation F is equals to d by dt integral v rho dv. Now here you see, this is one v where what we have done, we have made it a strike through. Okay, so we are writing the v with a strike through. And this is a v where we are not putting it a strike through. Why? Because there are two v's. One is the volume, other is the velocity. You just wanted to differentiate between the two. So here when we have the strike through v, that is basically the volume. The other one is the velocity. Okay. So we have integral v rho dv plus integral at the control surface rho v dot a. Okay. Now assume that each particle inside the control volume has the same velocity, then the first term on the right hand side could be written as. So in that case, the first, if each each fluid particle within the control volume has the same velocity. That means the velocity becomes constant. And if the velocity becomes constant, it can come out of the integral. Okay. So we have this velocity that becomes constant. It comes out of the integral. Okay. So we have our equation becomes this V integral rho dV. Now this integral rho dV over the entire control volume is basically the mass. Okay. So we can write this term. This term is basically the first term on the right hand side. We can write this term as d by dt of mv. mv is the momentum within the control. So rate of change of momentum inside the control volume. Rate of change of momentum inside the control volume. Okay. So this will be the accumulation term. Now let's discuss about the second term. Regarding the second term, it's discussed here. And assuming that the velocity is uniformly distributed as it crosses the control surfaces, then the last term on the right-hand side could be written like this. So this is the last term on the right-hand side. Okay. So this can be written as, because again, now this velocity is constant. So it can come out of the integral. Okay. So it is going to come out of the integral. So it becomes rho v dot a integral v. Okay. Then here this becomes the integral sign can be changed to summation sign. Okay. Because it depends upon how many inlets and outlets do we have along that control surface. Okay. And we are assuming that the velocity is uniformly distributed at any control surface. That means we can replace the integral sign with the summation sign. Okay. So here we have the summation sign here, just replacing it, replacing the integral sign with the summation sign. Okay. Now this is what is happening at the control surface. Now in the last class that we studied that there are two possibilities that momentum or the fluid can be going into the control volume, or it could be going out of the control volume through the control surface. So if we have this kind of situation, what we can do is that we can further subdivide, we can further differentiate those going into the control volume and the momentum going out of the control volume. So the momentum going out of the control volume would be considered as positive. Momentum going into the control volume will be considered as negative. Now, why this negative is there? This is something we discussed in the last class. Because this is a dot product of velocity and area, and whenever the fluid is going into the control volume, so the velocity and area both have the same direction, so it will be considered positive. Whenever the fluid is going out of the control, whenever a fluid is going out of the control volume, then the velocity and area have the same direction, so they're considered positive. Whenever the fluid is going into the control volume, the velocity is the inside has the inside direction, and the area will have the outside direction, because area is always directed outward. Okay, so we'll have an angle of 180 degree, and cos of 180 degree will be -1. So that's why always inlets are considered as negative. This is something that we discussed in the last class when we were discussing the Renault transport theorem. Okay. So we are going to have this last term, we can write it as like this. So now after modifying the right-hand side terms, our final equation becomes like this. This is our final equation. And this is the main equation which now we will be using throughout in our calculations, which is summation of all the forces. These are the external forces. We are not discussing about the internal forces. The external force, summation of all the external forces is equals to rate of change of momentum inside the control volume plus whatever the momentum of the fluid entering through the control surface into the control volume minus whatever the momentum is leaving the control volume through the control surface. Okay, so the momentum of the fluid coming in minus momentum of the fluid going out. Momentum of the fluid going out minus momentum of the fluid coming in, plus whatever the rate of change of momentum inside the control volume. This is going to be equal to the summation of all the forces, which are all the external forces, which are either acting on the fluid or acting by the fluid outside on something else. Okay. So these are some of this is the main equation, linear momentum equation, which we have developed by using the Renault transport theorem. Renault transport theorem, once again, to remind you, Renault transport theorem we developed in the last class. Okay, and I told you that this is a theorem that once developed, now we are going to use in the next 5 classes. So we used it in the continuity equation in the last class. Then we are using today in the momentum equation, Renault transport theorem. Then we will again use it in the momentum equation in the next class. Then we are going to use it to develop the energy equation in the next 2 classes. Okay, so this Renault transport theorem is something that we will be utilizing it for the next 5 classes throughout. Okay, so we have used it here to develop the momentum equation at this point. So in this equation, summation F are the net forces. So net forces are basically whatever the force that could be applied on the fluid, or sometimes the forces are being applied by the fluid. Like for example, if I have a jet of water and I throw it on the wall, the force will be applied by the jet of water on the wall. So that's an external force. Okay. So sometimes we have certain corners, some certain deviators through which we deviate the fluid motion. But those deviators actually feel the forces of the fluid as the fluid is being deviated. Okay. So we have the net force here. Then we have the momentum accumulation term. Most of the time in our calculations that we are going to use, the momentum accumulation term will be 0 in our calculation. There are cases where momentum accumulation term will not be 0, but mostly we are not going to cover that as a part of our course here. Okay. However, the net momentum flow terms, yes, definitely they will be there. So these two are the net momentum flow terms. This is the momentum accumulation term, and these are the net forces. Okay, and this is the significant or fundamental equation that we will be using. Okay, now this equation will be provided in exam without explaining all the terms mentioned here. Okay, so you need to know that what are these terminologies which are used here in this equation, but itself, even if you don't memorize this equation, this will be provided in the exam. Interpretation of the linear momentum equation. Application of the momentum equation to fluid flow problems is analogous to the use of the free body approach in solid mechanics. This is something that you have gone through it, solid mechanics, where you draw the free body diagram. So we draw the free body diagram by excluding our interest from the rest of the surroundings, okay, and mentioning just the forces. Let's talk about let's talk a little about the momentum accumulation term. This term, d by dt mcv vcv. Okay, this momentum accumulation term is 0 if 2 conditions are satisfied. Okay, the velocity and density of the fluid at each point are constant with time in the control volume, that is, the flow is steady. So whenever the flow is steady, so the momentum accumulation term will be 0. The second thing is that structural elements within the control volume are stationary. So if your structural elements are also not moving, then the momentum accumulation term will be 0. So mostly the problems that we are going to deal in this chapter here are the ones where the structural elements will be stationary and the flow will be steady. Okay, so that's why the momentum accumulation term will be 0. But if these 2 conditions are not satisfied, then the momentum accumulation term will not be 0. Okay, so what are the 2 conditions for which the momentum accumulation term will be 0. These are the two conditions, and I want you to memorize them. I can ask in short questions that write down the conditions for which the momentum accumulation term could be 0. Okay, so I provide you this main equation. And just ask you that, okay, write down the conditions for which momentum accumulation term is 0. Now, first of all, even if you have not gone through the lecture properly, you don't even know that which of the term is momentum accumulation term. So you should know which is the term is the momentum accumulation term. And then what are the reasons that could be 0? These are the two reasons that you have to then write. Even the whole statement is not important. If you just write that they will be 0 if the flow is steady and the structural elements are stationary. If you just write these two things, that will be enough. But if you write the whole story without mentioning the key verbs or the key terms which I'm looking for, then obviously you're not going to get the marks. Okay. So far, everything is clear. Now, visual solution method, VSM. Okay. In the visual solution method, the first thing is that what we do is, in order to solve the problem, we develop the free body diagram. Okay. And free body diagram means what? For example, this is a case that water is flowing through a bend. This is a pipe bend. Water is flowing through a pipe bend. And normally, you know that bends are separated from the pipe, and we attach them with the pipe. Now, if the bends are not welded with the pipe, there is another option. We can attach it with the help of flanges. Flanges could be used to attach any bend with the pipe. Okay. Now the flanges are screwed. So we have a flange in a pipe. We have a flange in a pipe bend, and then the two are brought together, and then there are holes. You can just screw them together. Okay. So suppose if they are not screwed and we make the water to flow through this pipe bend, so obviously the water is going to apply a certain amount of force over the pipe bend, and the pipe bend will displace from its position. Okay. So there is some force which is applied by the water as it passes through the pipe bend, and that force need to be countered so that the pipe bend stays in its same location without being displaced. Okay. So let's say that we have this situation that water is passing through the pipe bend. Okay. And it is going into the atmosphere. It will be the zero gauge pressure. Okay. So the first thing is that we draw the free body diagram. Now we'll have two free body diagrams that we have to draw. One will be for the force. This is known as the force diagram. In the force diagram, we are just going to draw our control volume and just show the forces. Okay, so here in this case, there will be the weight of the pipe bend which will be acting downward. Then we will have, because the fluid is coming from this end, so there will be some pressure in the fluid. Okay, so whatever the pressure of the fluid, so the force due to the pressure that is shown here, P1A1. So we are showing two forces here, weight and the force due to the pressure, and that's it. No other force. Whatever the force is, we just mentioned that, nothing else. Okay. Outside we have atmospheric pressure, but atmospheric pressure is considered zero gauge, so there will be no pressure, so no force corresponding to that. So the first is the force diagram. Okay. Then the next is the momentum diagram. In the momentum diagram, we just mentioned the flow. In the force diagram, we do not mention the flow. In the force diagram, we do not mention the flow, where the flow is coming, where the flow is going. But in the momentum diagram, we don't mention the forces, we just mention the flow. And the momentum with it, whether it's going into the control volume or going out of the control volume. So for example, in this case, there is momentum mv1, which is actually going into the control volume, and then momentum mv2, which is going out of the control volume from this point. So we have to draw two diagrams. One is the force diagram and other is the momentum diagram. The force diagram should mention the forces only without mentioning the flow and the momentum. The momentum diagram should not mention the forces. It should only mention the flow and the momentum. Okay. So whatever the fluids are entering into the control volume and whatever the fluids are moving out of the control volume. Okay. Is this thing clear? Now, when we are talking about linear momentum equation, so we have velocities and we have the forces here in this equation. And as we know that the velocity and force are both the vector quantities. So there's possibility that, and most of the time in the realistic problems are always three-dimensional problems. So there could be the components of these forces and velocities in the x direction. There could be component of these forces and velocities in y direction. And similarly, there could be component in the z direction. So that means we can develop three different equations corresponding to this singular momentum equation. So we can have this equation in the x direction. Then in that case, we are going to use summation fx and the velocity component in the x direction. Then in that case, other equations could be one in the y direction, one in the z direction. But in that case, the velocity component should be in the y direction and in the z direction. So this is just the same momentum equation when written for three different Cartesian coordinate systems. Problems, we can have different problems for different applications. We can have the problems with the stationary control volumes. We can have the problems with the moving control volumes. For the stationary control volumes, it could be the problem of jet and vanes. Then it could be the problem of nozzles and pipe bends, then variable velocities. For moving control volumes, it could be the constant velocity problems and it could be the accelerating problems. Okay. So there are different applications. Right now that we are going to cover in this course will be jets and vanes and nozzles and pipe bends only. The rest we are not covering in this course in the class, but they are there for you for self-study if you want to go through. Okay. But the things that we are going to cover in the class are the jets and vanes and nozzles and pipe bends. Okay. These are the applications of the momentum equation that we are going to cover. Now we have the topic of fluid jets, but let's have a break of 10 minutes and then we're going to start this topic.